Today's array playlist problem is 14. Longest common prefix. You are given an array of strings. Your task is to find the longest common prefix shared among all the strings in the array. A prefix means characters that appear at the beginning of each string in the same order. If no common prefix exists, you should return an empty string. Important points to remember. The prefix must be continuous from the start of every string. Even a single character can be a valid prefix. If the strings differ at the very first character, the answer is empty. This problem tests string comparison and careful iteration across multiple words. Let's understand the problem using examples. Example 1. We are given the strings flower, flow, and flight. Let's compare them character by character from the start. All three words start with F, so the prefix is F. The next character is L in all three strings, so now the prefix becomes FL. After that, the characters are different. Flower has O. Flow has O. Flight has I. Since they no longer match, we stop here. So, the longest common prefix is FL. Example 2. Now consider the strings dog, racecar, and car. Let's check the first character of each string. Dog starts with D. Racecar starts with R. Car starts with C. The very first characters are different. That means there is no common prefix at all. So, the correct output is an empty string. These examples clearly show how we compare strings from left to right and stop as soon as characters don't match. The big idea is to discover the elegant logic behind efficiently identifying the longest common prefix across a collection of strings. We'll use a smart approach that leverages sorting to simplify the problem dramatically. Why does this work? Stick around, it's genius once you see it. Here's the core insight. The longest common prefix, LCP, for all strings in the set is always the same as the common prefix between just two strings, the lexicographically smallest and the lexicographically largest ones. In other words, after sorting the array alphabetically, we only need to compare the first and last strings. Any prefix common to these extremes will be common to everything in between. This reduces a potentially complex problem to a simple comparison. Why does sorting help? Sorting arranges the strings in alphabetical, lexicographical order. This groups similar prefixes together. The first string becomes the smallest, and the last becomes the largest. The extremes are the most different, so their common prefix is the tightest bound, exactly what we need for the whole array. Visualize the alphabet exploding into order. That's what sorting does here. Step 1. Sort the list. Take an unsorted array like mint, mini, mineral. After sorting, mini, mineral, mint. Notice how mini is now first, smallest, and mint is last, largest, with mineral in between. Sorting places the extremes at the ends, ready for comparison. Now, steps 2 and 3. Isolate the first and last strings, then compare character by character. For mini and mint. Index 0. M equals M. Index 1. I equals I. Index 2. N equals N. Index 3. I equals T. We stop here. The common prefix is up to index 2, minute. This table shows exactly where they match and diverge. Visualizing it, see how minute is shared across mini, mineral, and mint. The divergence after N, IVST, sets the boundary. This confirms why comparing extremes works perfectly. Steps 4 and 5. Build the prefix from the matching characters, then return it. In our example, concatenate M plus I plus N minute. That's the longest common prefix for the entire array. Simple extraction, and we're done. Finally, efficiency gains. The naive way, comparing every string pairwise, is O(n*(m), which can be slow for large inputs. Our sorting plus comparison approach. Sorting is O(n log n), comparison is O(m), overall much better, especially with many strings. Look at this comparison. Naive hits 100% complexity load, optimized drops to around 30% in practice. Dramatic speed up. And let's see the full solution. We are given a list of strings, and our task is to find the longest prefix that is common to all of them. If no such prefix exists, we simply return an empty string. The key idea here is sorting. When we sort the list of words lexicographically, any common prefix shared by all strings must also be shared by the first word and the last word in the sorted list. Because these two words are the most different in dictionary order, if they match at some position, all words in between will also match at that position. So here's what we do. First, we sort the array of words. Then we pick the first word and the last word. Now we compare both words character by character, starting from index 0. If the characters match, we add that character to our answer. The moment we see a mismatch, we stop, because the common prefix ends there. Finally, we return the accumulated prefix. This approach avoids unnecessary comparisons and gives us a clean and efficient solution. Alright, now let's run the code. Running the test cases. Perfect. The output matches the expected result. Now let's hit submit. And there we go. Accepted successfully. All test cases passed. That's how you efficiently solve the longest common prefix problem using sorting. If this explanation helped you, don't forget to like, share, and subscribe. More clean and optimized LeetCode solutions coming soon.